Now we're going to look at derivatives and the instantaneous rate of change application. And just remember, so far we've looked at what I call the basic building blocks or the pillars of calculus and its limits and continuity. And now we're going to take advantage of those, although we're not going to get into the specifics, and we're going to look at calculus. And the first part of calculus we'll look at is the derivative, which, to give away the ending, is just the slope of a tangent line to a function. So if you have a function, looks like something like that, and you have a tangent point there, then you can find the slope of the tangent line. That's called the derivative. Now, let's just do a quick warm-up on limits. Make sure we've got this down. So here we're looking for the limit as x goes to 4 of a function, and the function in this case, if you wrote f of x, would be x over x minus 4. And so we say, oh, if x is 4 on the number line, there's 4, and you have 5 and 3. Then you can come at 4 from the right, or you can come at 4 from the left. And when you do that, if here's the function, we can plot some points and see if the y values, get closer and closer to something over here. So we have an x of 4. So let's try some 4s from the right. And the way we did this is we said 4, and just if you're not really into the theory, if you just kind of want to get through this class, then you just write the 4 plus each time up there and do the dollar, the dime, and the penny. 5, 4.1, and 4.01 are the numbers. These are getting closer to 4 on the x. And then also from the left, we can write the 4 minus above each one. And then dollar, dime, penny. So 4 from the left. So the left of 4 is 3. 10 cents away from 4 on the left is $3.90. And 1 penny from 4 on the left is $3.99. Those are getting closer and closer to 4. Or $4 if you like money. So then the y value, we plug it in. So if we have 5, we have 5 over 5 minus 4, which is 5 over 1. Well, that's just 5. If we have 4.1 and plug it in, we have 4.1 over 4.1 minus 4. So you have 2 x's, so we plug it in twice. So 4.1 over, subtract that, you have a tenth, and that's going to be 41. And you can plug in the other one yourself, but you'll end up with 401. And you can see these are not limiting to something like 3 or 0. They're getting larger and larger. The next one will probably be 4,001, then 40,001. They're going to infinity, actually, the trend. And then these guys, if you plug that in, so 3 over 3 minus 4, that's going to give you a 3 over minus 1, or minus 3. Plug in 3.9, 3.9. Again, we plug it in 2 times, because there are 2 x's in that function. So it's 3.9 over minus 0.1, and that's going to give us a minus 39. So you kind of see a trend probably already, minus 399. You can plug the last one in if you want, or another one even. And these, they're getting larger and larger, so they're going to infinity in magnitude, but they're negative. So they're actually going to negative infinity. And then to see if this limit of the function exists, we look at infinity and minus infinity. We say, oh, those are not the same, so the limit does not exist. And basically, in the picture, what's going on here is we have 4 out here, and what we're saying is, well, as we get closer and closer to 4 from the right, so from the right, the y values are getting larger and larger. So from the right, the y's are going up, and from the left, they're going down. So we have this horizontal asymptote here, and they're not going to the same place. So here, sometimes we have infinity. Remember on the number line, if we're looking at x go to infinity, infinity is not on the number line. We just take things like, I don't know, things from the left of infinity. We always start with 10 because we have 10 fingers, and it's a nice way with decimal numbers to make it work. So here are some numbers getting larger and larger, going to infinity by exponents. So 10, plug that in, 1 over 10 plus 2, and then plug the 100 in, 1 over 100 plus 2, and the 1,000 in, 1 over 1,002. Just figure out what those are, and they'll give you the numbers here. And I'll just quickly punch them in the calculator and write them in. So 1 divided by 12. Okay, try it again. 0.083 repeating or something like that. It's about 0.08 and then 1 over 102, 0.0098, and then 1 over 1002 is 1.00998. I give you things that give you interesting patterns a lot of times, but the thing to look at is this is got 1 0 there, and this has got 2 zeros, and this has got sorry, it's 3 zeros there, 3 zeros. So this is getting smaller. I'm sorry, it's not 1, it's 0. But anyway, so this is getting smaller and smaller. It's going to 0. So as the x's go to infinity, the y's go to 0. So in their picture, as and the x-axis, and here's the y, the altitude, as the x's go to infinity, these guys are going to get smaller and smaller. It's kind of like a drone landing. And then here's an interesting one that will be useful for the derivative. So here, instead of x, I used h, and the function is 0 over h. So I want h goes to 0, so we can have the limit as h goes to 0 from the right, and the limit as h goes to 0 from the left. And here's how we use it. So we'll put the h in, and then our function is 0 over h. So instead of y, I'm just going to write the 0 over h to make it a little more obvious what we're plugging into. I think I did it this way. Those are going to go to 0. And then the same thing here. Stylus challenge for me. And these are going to go to 0. So as h goes to 0 from the right, we'll have 0 plus. Maybe you don't want to mess with it. You're just going to write that in with the dollar, the dime, and the penny. And you say, oh yeah, that's that 1.1, 0.01 thing. And then you can write the 0 minuses here. Dollar, dime, penny. Oh yeah, minus 1, minus 0.1, or 1/10, and minus 1 100th, or 0.01. Now plug them in. So if you plug in 0 over h, and the h is 1, it's 0 over 1. Well, 0 divided by anything is 0. And then try the 0.1, so it's 0 over 0.1. Well, 0 divided by anything is going to be 0. You can do that on a calculator. 0 divided by 0.01, also 0. And the same thing here, 0 divided by negative 1. 0 divided by anything, even negative numbers, is always 0. So these will all be zeros. And this, are they limiting to anything if you look at it? And this is the thing I kind of talked about before, like it's so easy, it's hard a lot of times to see it because it's not really trending down. Like see how these are getting smaller and smaller. But maybe think of it this way. It's kind of like you're asking, at tonight, is it going to be at Walmart? And you say, well, let's say the person parked this morning at Walmart and their tire was flat, and they've been there all day. So each day it's 0. Each day they're at Walmart. Each time of the day it's at the person's at Walmart, and you say, are they going to be at Walmart tonight? And the answer is yes, because they can't go anywhere. So they've been there all day. It's already there, so we say it has limited to 0. It just happens to already be there. So these are the same. And if you have some trouble with these limits and accepting them, don't feel bad. The math community took 100 years to even accept limits and a lot of the calculus. So it's kind of like, is the Earth the center of the universe kind of thing back in the 16th and 17th century. All right, so that's an interesting problem with the 0 over h. Now let's look at the derivative. And you can spend a lot of time on the derivative. I'm going to give you a quick way to get up and running with it. And then we'll see. If you're really into it, maybe study it a little more, ask me a question. So the derivative, how it relates to the real world. Let's start with rates. A rate is a ratio of two different things. So you could have a rate as change in distance over change in time. That would be a velocity. Like I went 10 miles in 1 hour. That's a change in distance and a change in time. So you could say, oh, that's 10 miles per hour. Is kind of like the velocity there. So if you drove 50 miles in 30 minutes, how fast were you going? I'm just going to get you started thinking on this line. So, well, the change in distance is 50 miles. The change in time is 30 minutes, but I'm going to call that 0.5 hours, or 1/2 an hour. So we can use our little formula, distance equals rate times time. If you don't remember that, I'm just seeding it for later. But you can solve that. So, oh, that's distance over time. So we say, okay, the change in distance or change in time. The change in distance was 50. And the change in time was 1/2 an hour. Because I want hours, not minutes in this case. So it's 100. And logically, a lot of you will figure that out. You just say, oh, well, if in 30 minutes I went 50 miles, it's kind of like going in 60 minutes 100 miles. So you could have been going faster or slower during an instant. The 50 and the 30 are average speed. So this little right here is the average velocity or average speed. And some other rates, you can have, of course, the rate of velocity like we looked at. And you can also have acceleration. So if you think about your speedometer on your car, maybe it goes 10, 20, maybe in 2 seconds, you go from 10 miles per hour to 20 miles per hour. So you change 10 miles per hour in 2 seconds. Well, that's time and time again, but that's a called rate of acceleration. And then a rate of growth, you just have, change in weight over time or length over time. Usually time is something we look at a lot. You might ask, well, what if you have a ratio of two things that are the same? Like, what if I have $10 and compare it to $100? And that's what we call a proportion. And proportions often will say put in percent form because it's comparing the same units. All right, so considering the function f of x equals x squared, I'm going to ask you a very simple question here. First of all, what's f of x? And I'm not trying to be too simple, but sometimes it's confusing at the beginning of calculus. Say, oh, f of x is given. F of x is x squared. And then the other thing I'd like you to calculate is f of x plus h. And we'll have a little extra worksheet on this if you're having real trouble with it. But f of x plus h is, now what f does is it takes whatever you give it, and it takes it and raises it to the second power. So what do we give it? We give it x plus h, put that in parentheses, and it raises it to the second power. Now how do you calculate that? I think I already showed this a couple times, but I use the box method, x plus h times x plus h. You could use FOIL if you like. I use this method for another reason. We might have one later on that works. Xh and h squared. So we have x squared plus there's two xh's there, plus h squared. So we have x squared plus 2xh plus h squared. And just, you're going to see this several times, you might commit it to memory. So then here's just a big fraction, and I'm going to calculate it. So what do we have? We have a thing on the top, f of x plus h, and we're subtracting another thing on the top, f of x, and then we're dividing it by h. So here we have f of x plus h, well, we would calculate that, x squared plus 2xh plus h squared. And f of x we have is just x squared. And now you see that we have an x squared, and what this says is take the additive inverse of x squared, the thing that you add to x squared to make it 0. So x squared, and the thing you add to it to make 0 makes 0. So 2xh plus h squared. You'll notice in this problem there's an h in each term up here, which means you can cancel it. If you cancel the h down here, you have to take an h out of every term. So we're left with 2x plus h. Right, that's pretty nice. A lot of the ones I'll give you will cancel like that. Okay, so let's try another one that's a little more complicated. Instead of x squared, we have x squared minus 1. So what's f of x? You might want to pause it and just try it on your own. Okay, so x squared minus 1. And then x plus h, where the x was, we have x plus h now. And don't forget that minus 1. It takes whatever it is squared, squares it. So we gave it this, it squares it, and then it subtracts 1. And then this is what we calculated before, the x squared plus 2xh plus h squared, and then don't forget that minus 1. And then our big fraction, so we have something in the parentheses, it's x squared plus 2xh plus h squared minus 1 minus. And I would just encourage you, if you're having some trouble understanding this, because it does give people a lot of problems, just take some time and figure out how to do these. Even if you don't understand all the theory, make sure you understand how to do this f of x plus h. There's some really good math lab resources. I can give you some sheets to look at and things. Watch a video on YouTube or something. So x squared, you can see here we have the additive inverse of each thing in here. So there's an additive inverse of x squared. That'll cancel the x squared. And there's a minus 1 on both. In fact, you can see a minus 1 and the additive inverse of minus 1 will cancel. And we're left with 2xh plus h squared over h, which we can factor the h out again, 2x plus h. I thought it was a little confusing. Took an h out down there, so out of each term. Terms are things with separated by a minus or a plus in an expression, like on the top here. So there are two terms. It's interestingly the same expression for that fraction in this case. Okay, we know the average velocity or average rate of change is the slope of the secant line. So basically, if you have a function, let's say we're looking at time versus distance. You could create a distance graph, and maybe it's going something like this. It's a car slowing down. So probably should hit 0 there. Anyway, we can take 2 points on that line, and we can 2 points on that curve, and we can draw the line that connects them, and that's a slope of a secant line. But we might want to know on our curve, just given 1 point, what's the slope of the tangent? And the secret to calculus is we'll look at the limit of these secant lines as we move that second point closer and closer. The limit to the slope of the tangent line. And so this thing we see with the limit down here, or the definition of the derivative, that's that h equals 0. So you might think of it as, let's say we're interested in this little function here. And we're interested in the slope of the tangent line there. And we'll call that x. Then we can take a distance here, h. And this x value then will be x plus h, right? We took x and we went h more, so x plus h. And then this value up here, see if I can get rid of that. It wants me to save every so often up here. So this guy up here, we say, oh, this is x plus h, comma, f of x plus h. So the x value there is x plus h, and the y value is you plug in that x plus h. And then the same thing here, this point is x, comma, f of x. So this guy's even with f of x, and this guy's even with f of x plus h. So if you wanted the slope of that guy, you could see you just take the y2 for f of x plus h, subtract the y1, f of x. This is y2, if you will, and y1. And then divide it by the x2 with his x plus h minus the x1, which is x. Right? This is x2, and this is x1. And then those cancel. So you can see there's that little fraction we've been using right there. And then we just watch as h goes to 0. We shrink that h. That's what this is here. So that's the formula for the derivative. Or we also call it the instantaneous rate of change. So basically, like we talked about speed a little bit, this is your average speed, the secant line, and this right here is what the speedometer read at that point in time. If you like a physical explanation for it, better hit the save on. This thing's going to start asking every minute. So let's say we have a function that says, this is meters per second. So let's say that this is a speed function or velocity function, and it says at time, whatever the time is, it's always 4. So this is a pretty simple function. What it's saying is, well, at time t equals 3, the speed at time 3 will be 4. And if you give it, let's say at time 5, what's the speed going to be? It's going to be 4. And if the time, it's like in space, this is something just moving. Time minus 2, what's it going to be? It's just a stupid function. It's always going to give you 4. What's f of banana? If you give it a banana, it's going to say, well, the answer is 4, because it's really a simple function. So let's look at that guy. So here's something. F of something is always going to be 4, and f of something else, that's always going to be 4. And then if you take that guy, you have a limit as h goes to 0. And on top we have 0, and on the bottom h. And we did this on the first page of these notes, and we know that that is 0. So that limit exists, even though it's kind of hard to calculate, right? You can't plug 0 in. If you plug the 0 in for h, you'd have 0 over 0. That doesn't make sense. So we use the limit to figure it. And if you sort of think about this picture, this is basically y equals 4. So 1, 2, 3, 4. It's this horizontal line indicating velocity. So we'll have velocity and time. And what's the slope of any tangent line to it? If you think about it, look, pick that point. What's the slope of the tangent there? A tangent to any line is just the line itself. And what's the slope of this line? It's 0. It's not inclined or declined. So the slope of the tangent line at any point is 0. So let's try a little more complicated one. Here's a delicious one. So our function is x squared. So in this case, we're interested in the simple smile. And we're interested at the point 2. And the point on the function, if x is 2, here's x and y, or f of x. 2, what is the y value that goes with it? Well, you can plug that in. 2 squared is 4. So that's the point 2 comma 4. And we're interested in the slope of the tangent line, or the derivative, at that point where it touches it. So let's find it using the definition. Or we could also call it the instantaneous rate of change. So we say, f prime of x, or the derivative, is the limit as h goes to 0 of f of x plus h. This thing that we just remember, because you may not want to rederive it. So we need f of x plus h. Remember, f of x plus h. We know what f of x is. It's given. X plus h, we just plug in x plus h here. So it would be x plus h squared. This is one we already did, and that's that thing to memorize, or you could use the FOIL or the box method. So we have x squared plus 2xh plus h squared minus, and then f of x is just x squared over h. And that limit follows us each time. I'd love to plug that 0 in for h here, but you see we'll have division by 0, so we can't do that. Anyway, you see an x squared and then minus x squared. And usually on the ones I give you, at least on a test, everything should cancel on the top except for h's. So we have 2xh plus h squared over h. And now you see, can't plug the 0 in yet, but if we cancel some of those h's, we're left with 2x plus h. Now we no longer have division by 0, so we can just plug in the 0 for h. So 2x plus 0, which is 2x. And what this is saying is, given any x value, you can find the slope of the tangent line by multiplying that x value by 2. So our x value is 2. So f prime of 2 is 2x times 2, which is 4. So the slope of that line, the tangent, is 4 at the point 2 comma 4. It's crazy, right? So here's another one. Find the instantaneous rate of change of x squared minus 1 at x equals 3. So now we could just say, well, let's find f of x plus h real fast. Now we're going to need that one. 6 plus h squared is another one we worked already on maybe the second page. And so our little IROC is f prime of x is, don't forget the limit. We have to shrink that h down as we look at these slopes of secant lines. So I'll write this in. And I'm going to put these big brackets in there just to make it clear. So we have x squared plus 2xh plus h squared minus 1. That's the f of x plus h. Then anything worth learning is worth taking a little time to learn. This is a really impressive thing that not many people can do, to be honest. Even people that get through calculus, many of them can't do it. So here we have a few things that cancel. So it's probably worth your time to look at it. And the minus 1, just like we did on the other page. And we're left again with 2xh plus h squared over h, which is, cancel some h's out. 2x plus h. And now we can plug in the 0 for h. 2x plus 0 and 2x. And this says now x is 3. So f prime of 3. What's the slope of the tangent line at the point x is 3? 2 times 3, which is 6. You say, well, that's interesting. It was 2x, even though it's a different function, x squared and x squared minus 1, it's always 2x. And if you think about it, this function, what it really is saying is, here's what we had last time, x squared. X squared minus 1, it just moves it down to minus 1 and has the same function. So if you have a point on this function where that at that x. The similar point at this x, they have parallel slopes. So it would make sense that 2x is the same on both. And let's try doing a little average speed problem just in case I get too much fun with the derivatives. So f of x is 2x minus 1. So let's call this x1 and x2. We're going to use this little formula for slope. So for an average speed, we'll take x1 and x2 and we say, oh, we want y2, so that's f of x2. Let's plug in x2. And y1, we'll need that. That's plug in the x1. So plug in x2. x2 is 3. Plug that in. 2 times 3 minus 1, which is 5. And then f of x1, plug in the 1. So 2 times 1 minus 1 is 1. And so now we use our little formula from the old days. So we have 5 minus 1 on top, subtract the y's, and then on the bottom we subtract the x's, 3 minus 1, keeping them in order, 4 over 2, or 2. So the average speed of this guy is 2. There it is. You can almost pops right out of that because it is a line. It's pretty easy. And then instantaneous speed at x equals 2. So here we need the little formula. Let's see here. It's f of x plus h minus f of x over h. So f of x plus h, and this guy is going to be 2 times x plus h minus 1. 2x plus 2h. That's right, because this takes whatever you give it, multiplies it times 2, and subtracts 1. So I'm giving it all this, so it's going to take all this and multiply it times 2, or double it, and then subtract 1. So we have 2x plus 2h minus 1 is the f of x plus h. And then the f of x is 2x minus 1. These brackets are very important. Now you can see the 2x cancels. The minus 1 cancels, and we're left with limit as h goes to 0 of 2h. All that other stuff 0 over h. And now you see, oh, h's cancel. So we have limit as h goes to 0 of 2. Well, it doesn't matter what h is. There's nothing to plug in. It's just going to be 2. So in this case, a line is very simple, right? If you have a line, it's kind of like, it's actually the south of the x-axis. But here's a line. If you take 2 points and take the slope of that secant, if you will, it's the same line. And also if you have a line and you take the slope of the tangent line, it's a very simple case. It's the same line on top of itself. So kind of a simple case there, but here we did it using, and where x is 2, so it's 2 everywhere, so f prime of 2 is certainly 2 as well. And just a few ways to write derivative if you're reading literature. A function, remember, we can call it y or f of x. And its derivative, we often use this little apostrophe here. It's not a 1, it's an apostrophe. So y prime, we call it, or the change in y over the change in x, or dy dx. Or sometimes they'll call it just the derivative of y with a big D. Or they'll call it f prime, there's that prime again, of x, or just f prime. So they love the little prime, and the little apostrophe there. And then also a change in f with respect to x, or the change in f dx, or df dx, or d dxf, or the derivative with a big D of f. So here's how a problem's often stated. Of course, usually it doesn't have the 1, 2, 3, but they'll say find f prime of x, or the derivative, using the definition. And that's this. So whenever you see using the definition, this is the definition. So if it says use a definition, you usually write this first, because just, it's like somebody's coming from Mars, or from the forest, forest people or something. You're coming in and you're like, oh, let me show you this thing from calculus in the 18th century that was in a bunch of letters between Leibniz and Newton. Okay, so right here we have a limit in these things. So we need f of x and f of x plus h. F of x is given. F of x plus h. This is x plus h squared. Now I know we've already done this one, but I just want you to see how it's phrased. And then we plug it into the fraction. So go ahead and work it if you want. Pause this video and work it yourself. See if you just remember that 1, because it's very common problem to have. Over h, and then some things cancel. And you do need to write it again. I mean, you should not do that and the h's in the same fraction. Take the additive inverses off. Rewrite this guy. Go ahead and take a moment. We're talking about 20 seconds here. And then now we have some h's that we can cancel. Do one thing at a time. 2x plus h. And when you cancel this, you'll get a 1 on the bottom, and these will all be 1s. So that 1 on the bottom, you just divide by 1 and not leaving it in there. Then we can plug in the 0 for h. There's that 0, and anything plus 0 is itself. And this is the general form. So for any x value, we know the slope of the tangent line with that crazy function. So here's one with a little more algebra practice to get you warmed into it. 3 minus x squared. Let's find, we'll need f of x plus h. Well, it says, it doesn't say anything about the definition, but use the definition. So limit as h goes to 0 of f of x plus h. First we write the definition down. And the reason is there are several ways to define it. This is the most common way these days. All right, so f of x plus h is 3 minus, and then where the x is, we put x plus h. Right? 3 minus, and that was x, now it's x plus h. So 3 minus, and that's going to be x squared. This is an easy one we know, right? xh plus h squared. We need x plus h squared to get that, but it's actually going to make a bunch of negative terms. 3 minus x squared minus 2xh minus h squared. So here we have our limit as h goes to 0. And on the top we have 3 minus x squared minus 2xh minus h squared. That's f of x plus h. From it we subtract f of x, which is just 3 minus x squared. And this is not going to get worse this semester. This is about as rough as it gets if you're starting to get a little brain dead from the numbers. The 3's cancel and the x squareds. It's also an impressive thing to show people at the dinner table, you know, if they're like, hey, what are you learning in college? Limit h goes to 0. You can say, how about this? And they'll be like, ah, yeah, you do know some things. So it was a minus. All right, so what I did is I copied the minus 2xh and the minus h squared up here. And everything else canceled, became 0. And there's an h and everything that's left. What a coincidence. So I'll cancel the h with that, and the same guy cancels with something in each term. So h goes to 0 of minus 2x minus h. So now we can plug in the 0 for h, minus 2x minus 0, or minus 2x. This one's a little different. And if you think about it, that's a frown, because 3 minus x squared, if you remember. So you go up to 3, and you make a frown. That's 3 minus x squared. So it kind of makes sense here. Slope is going to be negative, right? In that case, unless you have a negative x. It's a positive slope. All right, so that was fun. Oh, it says x is 1 here too. So it wants the slope where x is 1. So here's where x is 1. We're going to want the slope of the line where x is 1. Well, we just plug it in. Minus f prime of 1 is minus 2 times 1. So minus 2. We know the slope of that line. It's amazing. And here's another problem. Given f of x is 3 minus x squared, find the slope of the tangent line where x is 2. We already did the work. Remember, f prime of x is minus 2x. I'm going to show you shortcuts so that we don't have to use a definition. That's just for now to start. So f prime of 2, we just plug it in. Minus 2 times 2 would be minus 4. So you can find the slope of the tangent line also in this case. So we have this as maybe not the best picture of 3 minus x squared. But if we go out here to 2, the slope of the tangent line is minus 4. And it makes sense. It's a negative slope. And then here's a sort of a challenge function down here. This is a little bit of an algebra exercise. So if we want f of x plus h, you might want to just pause it here and give it a shot on your own. So to where the x was, we put an x plus h. and then squared, and then minus, and then where the x is, I put another x plus h. See how I put the little parentheses to show, and that'll be good for this minus. And then plus 1. So see, I just replaced the x's with an x plus h. That's all I did. And so you remember from our little thing, we know that this squared, square first, then times 2, x squared plus 2xh plus h squared. And then distribute the minuses through, minus x minus h plus 1. And so what we have is, put the 2, it's like a super distribute problem here. 2x squared plus 4xh plus 2h squared minus x minus h plus 1. So it sounds awful, but it's cathartic because, let's see here, I want f prime of x. So that's going to be the limit as h goes to 0 of, here's the definition. It says to use the definition up here. Minus f of x over h. So limit as h goes to 0. On the top we have f of x plus h. It's nightmare right here, all this stuff. None of them are like terms. 4xh plus 2h squared minus x minus h plus 1. And then subtract f of x, which was what we were originally given, 2x squared minus x plus 1. You can kind of see we want that because we want some things to cancel. And then over h. So I still have a limit. So we can't plug the 0 in to a denominator. So 2x squared cancels with 2x squared. Just look over here. There's a minus x. That's the additive inverse of minus x. And 1, the additive inverse of 1. That's what that minus in front means. So all those things cancel. We're left with, there's a 4xh in there, and a 2h squared, and a minus h, all over h. And what a coincidence. There's an h in each term, so we can cancel this guy with one of each of those terms. So we have 4x plus 2h, and then when that cancels it becomes a 1, so minus 1 over 1, really. So then we can plug the 0 in for h. So we just have 4x plus 2 times 0 minus 1, which is 4x minus 1. That was a little different. But that will give you the slope of the tangent line at any point. So that one's shifted over a little bit or whatever. It's a smile. Just, if you want the slope of a tangent line, just find the x that lines up with it, and you can plug it into that expression and get the slope of the tangent line. It's very powerful. Okay, so let's just think about this for a moment. This guy here, like that whole definition is very complicated with x plus h and everything. But if we had a way to find that quickly, find the derivative really fast by using some tricks, then let's say we found it to be this. F of prime of x is 4x. And that's what we're going to work on is tricks and techniques. That's going to be the next couple of weeks here. Tips and tricks to find fast derivatives. But if you have it, now if you know x is 3, then you can plug in the 3 right here, and you'll get 19, right? Because 3 into this is 2 times 3 squared plus 1. So you know 3 comma 19, the y that goes with the x 3 is 319. Then you can find the slope of the tangent line also just from using the x, because it's 4 times x, so it's 4 times 3. So the slope is 12. In fact, it's easier, isn't it, to find the slope of the tangent line than to find the y value, because this thing lost some of the power there. So it's just very powerful. And then this guy here looked something like, this steep guy. And we said, oh, at 3, you can find the point 19 is on the graph, so that's 3 comma 19. It was hard to find the 19, right? Plug it into that. 9 times 2, 18 plus 1. But then the slope of the tangent line, if you're given any slope is 4x, you just plug it in. 4 times 3, 12, done. So the slope of that line is 12. And is this function a low, medium, or high maintenance friend, do you think? You notice it doesn't have any division or square roots. It's smooth and continuous when I graphed it. It's a low maintenance guy. It's the end of the lesson.